Hello there, and welcome to the second of three presentations in this series that we've called Emerging Pieces in the COVID-19 Puzzle, with myself, Rob Thomas, as your host, in conversation with Dr. Christine Houghton, a nutritional biochemist and an educator in the science of clinical nutrigenomics. Now, the professional education division of Christine's company, Cellular, has sponsored this series, reviewing some of the very puzzling questions surrounding COVID-19. Now, across the three sessions, we take a close look at the various ways the virus attacks our cells. But in this episode 2, we review the remarkable inbuilt processes our cells use to fight back. Then in the final episode, we'll tie it all together and provide some practical solutions any of us are able to implement. Welcome, Christine.
Thank you, Robert. It's a pleasure to be back again. And we covered a lot of ground last episode, and I'm thinking we're probably going to do the same thing again.
I think we might. And actually, Christine, in this episode 2, as I mentioned, we're going to be looking at some of the inbuilt immune processes that enable us to fight back against a viral attack, and in this instance, particularly COVID-19. Now, but before we discuss how this happens, can you perhaps briefly recap what we discussed in episode 1?
Yes, I think we should. So essentially what we looked at was the fact that there are a couple of different ways that the virus causes so much damage to human cells. And I'd just like to backtrack a little bit by looking at one of the slides that we looked at last week, just to give us a clue as to what happens. So if we look at, here's a COVID-2 virus with its little spikes around the outside and its single strand of RNA. But we also talked about the fact that that virus cannot replicate or multiply in any way by itself unless it hijacks essentially the processes of the human or other animal cells. So what happens here is we have on our own cells these little ACE2 receptors, and the spikes fit in like a lock and key mechanism into that receptor. And that's step 1. Now, I think what's not coming across particularly well in the popular discussions on this is just the fact that the virus attaches to the receptor does nothing. It needs the assistance of this protease enzyme with a funny looking name, TMPRSS2, and what it does, it actually breaks up the spike and then allows the membrane of the virus to fuse with the membrane of the host cell, and that's what allows it to get into the cell. So that's the first place that we cause damage, not only by letting the virus in, but because ACE2, as we learned last episode, is actually a protective molecule, and now it gets broken down in the process of getting the virus in, and there's step 1, starting the process of damage to humans. Now, the other thing that causes us lots of damage is its effect on the hemoglobin molecule. So there's a hemoglobin molecule. That's the iron-containing molecule that carries oxygen around the body and into cells. So now the COVID-2 virus attacks one of those protein chains of the hemoglobin. That tends to smash part of the hemoglobin molecule apart. That lets the iron out and released into the environment. And iron, if it's not bound up, there's an iron, is quite damaging, produces free radicals, which we call reactive oxygen species, and inflammatory cytokines, all very damaging. Now at the same time, the cells can't get as much oxygen as they need. So now we get the oxygen starvation, which leads to an inability to breathe and major lung damage and lots of scarring. So that in a nutshell is what we discussed last week as the major reasons that the virus causes the damage.
It's quite an insidious process. So, and along with this, Christine, there's a huge amount of confusion and really misinformation also around appropriate ways to approach the prevention and appropriate treatments for those who've contracted COVID-19. Now, I know the immune system's enormously complex, but can you just give us a really brief overview of how it works?
Yes, so you're just going to get a tiny little snapshot here of what really happens. So the immune system itself acts in every part of the body, and it's made up of two main divisions, an innate immune system and an adaptive immune system. And what we need to know from this is the innate immune system is operating all day, every day, whether or not there's any threat of infection going on. So these particular specialised cells here, we'll talk about natural killer cells later, because as their name suggests, they're pretty nasty guys. If you're a virus, they're one of our main immune cells that kill the virus. This little fellow here, the neutrophil, it's the one that gets there first. So as soon as there's a threat, it's on the job and sending signals out to recruit in its other mates from the innate immune system. So when there's a threat of any sort of an infection, it could be a bacteria, a virus, parasite, anything, almost immediately the innate immune system jumps to action. So that's happening within hours. But then as the infection progresses, if the innate immune system can't get rid of some fairly harmless little microbe, we ramp up the defences. So over time, and this is probably likely to be days and even up to a week before we kick into the adaptive immunity. And that's, so we've got hours over here. The adaptive immunity is the one that I think a lot of people are talking about in connection with COVID-19, because it's here that we produce antibodies. So those little Y-shaped things are designated as antibodies. And they have been manufactured by our cells specifically for that virus. So over here in the innate system, they don't particularly care what the name of the organism is or what it does. They just know it's a guy they need to get rid of. It'll be better if we don't have it. As the days go on, complexities develop and signalling increases such that we're producing antibodies. Now, what's interesting about this is if there is ever a vaccine developed against this particular virus, COVID-2, it is our cells which are going to accept some sort of an antigen or a stimulus that tells our immune system that it must make these antibodies. So the vaccine is not the antibodies. The vaccine is just a signal to tell us to make our own antibodies. And you've sometimes heard that there are people who don't respond to a vaccine, and particularly elderly people. And that's typically thought that that's because all these initial parts of the immune system over here are not functioning as they should, and therefore those people can't mount an appropriate defense and they can't make the antibodies. So that's essentially the difference in the two parts of the immune system. For our purposes here, we're going to concentrate on what we can do for innate immunity, because if we can get in early, let's not wait for days and up to a week to go by. We need to be attacking this virus as soon as possible, and even to stop it getting in the first place. If it does get in, there are things we can do, and it's this innate immunity that we have most control over. And particularly in episode 3, we're going to discuss the various ways in which humans can influence the way in which this innate immunity is functioning. So there's our natural killer cells. And these little dotty bits in here, these are granules, and these are highly toxic granules. So when they engulf the virus, they basically poison it, smash it up into bits, poison it. But at the same time, we will have a cell of our own now that's infected with multiple viruses that gets killed. So we're producing a lot of debris at the same time as we're killing the virus. And that's one of the intricacies of a naturally healthy immune system, is that it knows how to kill the virus, but at the same time, not to kill too many of our own cells.
Yeah, isn't it wonderful? And it's interesting with the immune system. It's almost that the innate, I almost see like the front line or the first line of defence. And then in that too, I want to ask you something later about, you know, there's a front line defence in there as well, you know, heading up that first line defence. I just find it remarkable. But I know over the last year, Christine, you've spoken a lot about this, and you've spoken and introduced me and many practitioners throughout Australia and New Zealand to the term and the concept of the gut immune interface. Now, in this interplay at the gut immune interface, the microbiota also play a vital role. So can you just talk to us a little bit about the microbiota, both at the gut and also in the lungs as well?
Well, I think a lot of people now are familiar with this idea of the microbiome. So it's got something to do with the good bugs that live in the gut. But what's become apparent over the last couple of decades is what's going on in the gut is largely controlling what's going on in the rest of the body. And it adds a completely new dimension, not only to what we think of the immune system, but what we think of managing disease in general. So if we just look at the next slide here, we're talking here about what we call the gut-lung axis. So we've got the gut in here, and of course this is where most of the microbes are living, and here in the lungs, smaller amounts. So all that diagram is supposed to show you is that we have microbes living in the lung, we have them living in the gut. And just because we have microbes in our system doesn't mean they're pathogens or they're toxic to us. We have whole families of trillions of friendly microbes. The problem is when the pathogens sneak in. So it's the job of these friendly microbes in the gut, to a large extent, to keep the bad guys out. And similarly, but to a lesser extent in the lung, we have that happening as well. And what this diagram is showing here is there's a constant interconnection between what's going on in the gut and what's going on in the lung. So you might think you're going to treat a respiratory virus and it doesn't matter what's going on in the gut. We're dealing with a virus that's affecting our lungs and our inability to breathe. But it's not true. And in episode 3, part of what I want to talk about in detail is how we can, among other things, influence what's going on in the gut microbiome so that we can impact what's going on in the lung microbiota.
Fantastic. So a little bit going back to the immune response too. I know you mentioned last time that there were 4 steps, you know, starting with recognition of how our immune system needs to respond. And I know what's coming home to me is that it's really this initial phase of our response and even recognition that is so important if anyone is to either not be affected at all or to be able to deal with this insidious COVID-19. So yeah, can you just quickly run through that one again too, please, Christine?
Well, to me, it's terribly important to understand the mechanisms that are going on in order that we can create some sort of a medicine or an approach in order to deal with these infections. And I think understanding those mechanisms gives us a number of points at which to intervene. And I know in pharmaceutical investigation and looking for drug cures, these same pathways are target points in drug manufacture, but I think it's becoming unnecessarily complex to look at a drug when often the solutions are right here. Now, I'll show you what I mean, because, one moment there. So if we're going to talk about these 4 steps to immune defense that you mentioned and we discussed last week. So here's our little cluster of COVID-2 viruses here, and here's some ACE2 receptors and so on. So what happens is this. First thing your body has to do is it has to detect a threat. It doesn't know what it is, but it does know, you know, it's like you're in your house, there's a noise outside, I better lock the door, I better peep out the window, I don't know what's out there. So in the second stage, the immune system has very sophisticated ways of identifying that that threat is a virus or a bacterium or whatever else. So there's all sorts of clever chemical signaling going on within the cells that allows the cells to say, okay, we figured you out, you're a virus, so therefore we need to mount a certain kind of attack to get rid of this virus. So then there are specific viral attack processes that are brought into play. And just as importantly as killing the virus is the ability to shut that attack down. And I think this step's getting overlooked to a large extent in a lot of discussions that I'm hearing, because we have no ability as clinicians to micromanage any of these steps along the way. All we can do is assist Mother Nature to go through all of the signalling processes, and importantly, to monitor when has the viral load been killed or adequately controlled, that we can shut this down. Because as we discussed last time, if we don't shut down this attack on time, the inflammatory cytokines and the reactive oxygen species now continue on to damage our own tissue. And that's where people are getting into these cases where we talk about a cytokine storm, and then we talk about pulmonary fibrosis, where the scar tissue sets in, we get clots going on. All of this is not just happening in the lungs. All of this, if it gets out of control, is happening throughout the body. And we've heard that the kidneys are very prone. The blood vessels are also very prone to this, and that's where the clotting comes from. So it's a pretty intricate sort of a process that's going on there. And really, we just need to let Mother Nature take over, give her the tools she needs to deal with this, and just sit back and don't try to micromanage these individual processes. As we mentioned in episode 1, thinking now we've decided the virus is controlled and we'll shut it down with anti-inflammatory drugs, it doesn't work, and it can't work, because it's about these constant feedback cycles that are going on, where the cells within the immune system are continuing to talk to each other backwards and forwards, fine-tuning every moment of every day that this is going on.
Yeah, it's incredible, isn't it? I must admit, as an advocate and a practitioner of natural medicine, I find these built-in mechanisms, be it the endogenous defences within the cells or the innate, front line, as I call them, and first line defences, very, very exciting. And that our body does have these mechanisms to fight back, to overcome, or to resist, infections like this. Now, Christine, given this, can you walk us through some of these remarkable mechanisms that are present in just the lung epithelial cells?
Certainly. So if we move on here, so here we have, so obviously a side view of the lungs. The alveoli are the tiny little parts at the bottom of the lung where we're exchanging oxygen and so on. So here's a blown up version. So these funny little blue things here are what we call cilia. These are the epithelial lining cells of the lung that line every tube within the lungs. And these little cilia are like hairs. And these little hairs are constantly washing things from the lung towards the outside. So there's a mucus secretion or a mucin layer there. So it's like a thick gel. And if any particles get trapped within that mucin layer, the cilia are constantly washing them out towards the outside to get rid of them. As an aside here, smokers have very few cilia remaining in their lungs, which puts them at greater risk. So here, just showing in this diagram, we've got some little spiky viruses here. So there's a COVID-2, let's say. But what we've also got here, these little yellow dotty bits are what we call beta defensins. So they're little antimicrobial molecules that healthy immune cells are constantly making. And we'll look at them a little bit later as well, because they're so important. So this is like, well, I hesitate to say antibiotic, because antibiotics don't kill viruses, but they're a very powerful antimicrobial chemical. If that were a bacteria, the beta defensins kill the bacteria, but these beta defensins also kill viruses. So part of the body recognizing this threat is a virus says, okay, let's make lots of these defensins that we know can kill viruses. So that's a very important part of the immune defenses. And then down here, we've got a chemical called secretory IgA. That stands for immunoglobulin A. Down inside the immune cells, cells called plasma cells, and their job is to produce secretory IgA. Now, they're doing that all the time. They don't care whether that's a bacteria or virus or nothing much at all. But secretory IgA is, again, a backup to the beta defensins. So I've named there just two chemical entities which can kill viruses, but there are many more. And I'm just going to go through these briefly because there's a long list and my list is still only brief. So these are the inbuilt defenses that are just sitting there ready and waiting if your immune system is healthy. So we mentioned the mucin layer. The secretory IgA, that's a chemical entity that's killing off pathogens. The cilia are important to wash out whatever's accumulating. And there are receptors. All these cells have receptors, the lock and key idea that it can attach to the virus or the virus can attach to it, and that sets off other signals. There are many other antimicrobial proteins. And then there are the inflammation promoting molecules, the free radicals that destroy pathogens, the natural killer cells and other types of killer cells which specifically engulf a virus and kill it. And then there's the protective ACE2 receptors, which we saw earlier, which should be sitting happily there on the surface of these lung epithelial cells, but of course get damaged as well by the virus. And then we've got antiproteases that tend to deactivate these proteases, which are the thing that the virus is creating, and more. So it looks a bit complicated there, but the point of this was simply to say we have so many inbuilt defenses and we need to know how to utilize them without waiting for someone to create a drug that's going to get us out of trouble. We can get ourselves out of a lot of this trouble by ensuring that our immune system's working this way.
Yeah, it's interesting, isn't it? I just find so it's almost like you've got the mucin layers to slow down whatever's coming in, and then allows these beta defensins and the secretory IgA to take care of it, so that it doesn't even get into the body if things are working well. And then that mechanism at the ACE2 inhibitors stop it from getting in through into the membrane. So look, I've actually written something down. I want to read it, and I've written down, it's like an orchestra playing an immensely intricate, complex and powerful symphony where each instrument is vital to get the whole thing right. And I just think it's absolutely wonderful. But given this, I know we're going to cover it in the final episode, Christine, but can you give us a clue as to some of the ways in which the body can favourably influence these remarkable orchestrated instruments of defence in our body?
Well, I like the orchestra analogy as well, because it's very finely tuned and all the instruments have to play at the right time, and they also have to stop playing when they're no longer required. Let's just move on and just have a look at these defences again. So here again we've got the lung epithelium, and with its little cilia attached. We've got these special goblet cells, and all they do all day is produce mucin. And so there, as we saw before, we're getting pathogens just trapped in the mucus. And I should say too, this doesn't have to be about a virus like COVID-2. This could just be some dust particles that you breathed in the garden and your body knows they shouldn't be there. They may have a few odd germs attached to them. So that process is going on all the time, but it has to be ramped up when there's a major threat. And So those two cells. Then we've got our antimicrobial peptides over here. So there's a cell called a Paneth cell, doesn't matter what its name is, but it's the one that produces these antimicrobial molecules that are killing off the virus. And of course, the reactive oxygen species, etc. So they're what we call the free radicals. And they also play a very powerful role in dealing with any sort of infection. I must say too in this context that because we're talking about free radicals being involved in direct antimicrobial killing, there's a temptation to think, well, I'll just get some antioxidants and I'll deal with it in that way. And as we're going to see later, that actually doesn't work. The antioxidant vitamins that we're familiar with are simply not powerful enough to deal with this process. Our body makes its own antioxidant enzymes, which are literally millions of times more powerful than the antioxidants that are coming from food and supplements. But we'll get to that a little later on.
So I believe too, and I'm sure you'll cover that, Christine, that there's some very good evidence to suggest that high doses of these manufactured vitamins can actually inhibit these built-in processes as well. So going back a little way, the forefathers of natural medicine, they were using things like, diet and of course, and lots of fruit and vegetables and exercise and saunas and fasting. So what do these things have in common? What is it about them in relation to these beautiful, this orchestra, that if it's playing, boy, it's able to almost overcome anything.
Well, when we talk about fruit and vegetables, I think we think in terms of vitamins and minerals and so on, and that's true. Fruits and vegetables are a wonderful source of those nutrients, but fruits and vegetables are also very important sources of phytochemicals, which actually we consider as signalling molecules. And the area that I work in to a large extent, nutrigenomics, which is nutra as in food, genomics as in gene, means food molecules that talk to your genes. So apart from the essential benefit of vitamins and minerals, we need these signalling molecules that are switching on part of our protective defenses within our cell. And that's a fairly new concept. The last 20, 25 years, we've come to see that food is so much more than just what you're going to get in a vitamin pill. And I think it's completely expanded the way we must look at nutrition as therapy. So I would like to go on and, when I find this slide, have a look at this idea of how diet and lifestyle actually influence cellular switches. So over here on the left, we've got some gut epithelial cells. So this is typically what would line the gut. In the small intestine, you've got these little raised up parts which increase the absorptive surface so we can absorb more food. But also, always in the gut are millions of microbes. There's a couple of happy little bacteria minding their own business. Here's a couple of viruses. Here's a little parasite. And here's a couple of the ACE2 receptors shown here. Now, if you go over to the other side, we've got the respiratory epithelial cells, which are in the lungs and all of the respiratory passages. And you'll see it actually doesn't look very much different, except we've got these cilia that are here. And in both cases, we've got, well, this is representing the immune cell network below. So they're both hollow tubes in the gut and in the lungs, and they behave in a similar fashion. So these cells are all activated by switches. Some switches turn up protective processes, some switches turn up inflammatory processes, but we're just going to talk about one general switch at the moment. So if we look over on this side, there are dietary factors which play a huge role on how these cellular switches operate. So here's healthy fruit and vegetables. Here's junk food, what else can I call it? Overly processed nutrient devoid food. The fruit and vegetables tends to switch on the protective mechanisms. The junk food, which is very low in these protective phytochemicals, tends to switch on inflammatory pathways. And so when we're talking about the value of eating a good diet, it's largely about avoiding processed nutrient devoid foods and eating more of these foods. The other sorts of things that can influence these switches is exercise. So when you go for a run, you're breathing more oxygen, you're generating more energy, you're producing more free radicals. And so that sends a signal to your cells that says, you better ramp up your defenses here, because you keep running like that, you might cause us some damage to our muscle cells. So that's a signal which activates these defenses. Environmental factors, that could be some ultraviolet radiation. And so our bodies are constantly looking for signals in the environment which can activate defense processes. So the juggle always is that we're trying to create this balance where we're increasing our defenses and down-regulating our inflammatory processes. So it's quite interesting, because when we look at the defensive processes, there's a whole lot of core processes that every cell needs to function, and it doesn't matter whether it's one of these gut cells, a respiratory cell, an immune cell, or perhaps even the cells of your skin or your eyes or anywhere else. So a core process then is to activate multiple cell protective defense mechanisms. And I mentioned earlier the idea of antioxidant vitamins being too weak to achieve very much in terms of shutting down prolonged inflammation, but these antioxidant enzymes are switched on when we activate these defense switches. The anti-inflammatory molecules or the anti-inflammatory cytokines are also modulated by these defenses, just enough inflammation to control a threat, but not so much to cause damage. Energy production is also essential in that way. If you don't have your cells producing enough energy, nothing much works. And the detoxification molecules are also very important, because even when you're controlling a threat of a virus, let's say, you are breaking down good cells as well. So when the virus has attacked your host cells, those cells are going to be killed off in order to get rid of all of the cell debris. So we need healthy detoxification pathways. And you just saw some little antimicrobial molecules creeping up here to the surface to deal with the specific threat. So that's sort of a bit of an idea of how our cells manage to defend themselves in a general sense. Whether there's an infection there or not, that's how healthy cells deal with any kind of threat that's happening anytime, all day. Could be sitting next to somebody smoking cigarettes and you're inhaling that cigarette smoke. Your defenses ramp up and they go, whoa, this will cause my lungs damage. I know how to deal with this. I'll switch on all these protective mechanisms. So that's what cellular defense is all about. In a nutshell.
Interesting. Very good. Thanks, Christine. And I know, as you know, which I spoke earlier about, you know, the gut, you're introducing the gut immune interface. And the more I've looked at this and spoken about it over the past year, I've thought that really these cells, the epithelial cells lying in the gut, probably face or exposed to the greatest amount and intensity of stressors of any cells in the whole body. I'm changing my mind a little bit. The lungs are obviously exposed to, you know, an equal amount of threat, because they're so close to this hostile external world, but they're also given the responsibility of this constant exchange of oxygen in and carbon dioxide out. So, you know, they've got to be, oh, well, what a job, you know, really. So what are some of the, again, some of the specific mechanisms are present in the lung that is going to help them? And if I can just say there too, when you spoke about those antioxidant defenses and anti-inflammatory to defend themselves, the cells themselves, How important is this to the cells lining the lung and lining the gut? You know, just so important. But yeah, what are some of those other mechanisms in the lung?
Well, it's absolutely critical, of course, that the lung can produce enough of its own antioxidant enzymes. So there's a couple of antioxidant enzymes that are at core, and one of them is superoxide dismutase. And that its job is to be sure that any oxygen-based free radicals are broken down before they do any damage. And interestingly, the lung is rich in this superoxide dismutase enzyme, which makes sense. And as I was saying before, these antioxidant enzymes are literally millions of times more powerful than an antioxidant supplement like a vitamin. But let me just go back to the slide we were looking at a moment ago. And what crept up here when you weren't watching, above this cellular switch, is a little image, and that's a broccoli sprout there. So in terms of looking for concentrated ways to activate these switches, there is a molecule present in broccoli vegetable, and it's much more concentrated in the broccoli sprout. So if we just backtrack a little and go, well, okay, how do I activate these cellular switches? So I can eat lots of fruits and vegetables. And the sad reality is most of us don't eat anywhere enough. In Australia, it's something like 6% of Australian adults eat the required quantities of fruits and vegetables daily. If we were to eat the required amounts, we would readily activate these switches when we need to. Sad reality, we don't. When we exercise, we are also activating these switches. A more concentrated way to achieve what the appropriate level of vegetables would be to eat cruciferous vegetables. So that's the broccoli family, cabbage, cauliflower, Brussels sprouts, those sorts of foods. But if you eat the sprout is more concentrated. So that's one of the ways in which we can activate those defenses. So in answer to your question about the specifics, I'm going to come back to the broccoli sprout in a moment, because there's part of the mechanism that we can use to defend ourselves embedded here. So in episode 1, we looked at the way the virus attaches to the ACE2 receptor, and then, and only then, with the benefit of this protease enzyme, this TMPRSS2, that now tends to dissolve the viral membrane and snap off the ACE2 receptor, that's what that is there, broken in half, and enables the virus membrane and the cell membrane now to fuse and allows the virus in. So that's what we're looking at here. Now, interestingly, Mother Nature has created this lovely balance arrangement where you have embedded in the membranes of your cells this SLPI, secretory leukocyte protease inhibitor, and that enzyme blocks this protease enzyme. So we can attach the virus to the membrane on the ACE2 receptor, but that does nothing unless this protease now breaks off the spike of the virus and allows it in. So if we need the protease to activate the viral spike, now we need to counter that by using this protease inhibitor. So I think that's fascinating. And there's a whole area of research which is based on looking at the balance between these proteases and the antiproteases. So interestingly enough, that enzyme is controlled by the same cellular switch that controls cellular defense mechanisms. And as it turns out, sulforaphane, the bioactive molecule from broccoli sprouts, is known to be the most potent of the activators of this cellular switch. And so we would hypothesize, because no one's done the study on this yet, but we would hypothesize that adequate sulforaphane will activate that defense switch which will activate the inhibitor, which will stop the protease from activating the entry of the virus into the cells. Now, when I say hypothesize, it's actually a little more than that, because in drug discovery at the moment, there are already in development some drugs which are SLPIs. These are the antiproteases. There's a couple of them being developed now, Camastat, which is developed for another condition, but unfortunately it comes with a whole host of adverse effects, so it's considered at the moment not to really be an adequate therapy in this context. And there's the research which was just published not so very long ago, which is showing that sulforaphane, the broccoli sprout bioactive ingredient, is capable of inducing that secretion in the nasal mucosa. And as you remember, the nasal passages are very richly supplied with ACE2 receptors, so and so is the tongue. And so we know that those are major entry points for the virus.
Isn't that interesting? So it's these inhibitors, these protease inhibitors, are like guards at the defence, at the gateway, or and they're there to stop the entry of anyone that maybe, or anything that may cause harm. So what about Christine? I know the good bacteria, and I've been introduced to a compound called lipoteichoic acid. What role does that play in this defence?
So I started off speaking about the role of the microbiome and how we become aware that the microbiome is very important for normal immune function. And I think it's time we tied that into our story of what's going on in the lungs. So if we just move on to our last slide. It's entitled How Good Microbes Send Immune Signals. So we're looking here at the respiratory epithelial cells, and there's our cellular again, and here's our immune cells underneath there. So if we have our lung respiratory passages that contain all of the normal healthy bacteria, we call them commensal bacteria. Those bacteria, and in this example we'll use lactobacilli because lots of people are familiar with that, because that's one of the major bacteria that's found in yogurt and kefir and other fermented foods like that. So we'll use that as an example. And those bacteria have a little molecule called lipoteichoic acid, you mentioned before, we just call LTA, sitting on their surface. And that little molecule sends a signal to our immune system. So here's the respiratory epithelium, here's the immune cells underneath. We need to get a message from that probiotic bacterium down through the respiratory cells and into the immune cells underneath. So here's how it works. Sitting on the surface of these respiratory cells are receptors. In this case, they're toll-like receptors. And these toll-like receptors now are the nice little key for, or the lock for the LTA key. And that now sends a message once it's locked into the immune cells below. So there's a macrophage, which is just one of the white blood cells that makes up the immune cells. And as soon as we do that, we produce a molecule called interferon beta. Now, in the conversation about virus control, the interferons are major molecules which are part of the viral control process. So it's a good thing for us to be able to produce interferon beta. And it then activates some cytotoxic lymphocytes, which is just a flash way of saying white blood cells that kill toxic cells. So now we've got interferon beta, which is capable of directly killing some of those cells. This signal from the probiotic bacteria does some other things. We have these T helper cells, which are just sitting there within the immune system, minding their own business, waiting for a job. And in this case, the job is to convert them into Th1 cells. And Th1 cells are very important cells in infection control. So then the next signal is that Th1 cells produce interferon gamma. And that's another one of these viral control signals. And I mentioned right at the beginning, we'd be coming back to natural killer cells. And they were part of that list of cells which make up the innate immune system. So they're naturally occurring. But when it's time to ramp up their quantity, here's how we can do that. So the signaling is really quite fascinating, that nature has multiple ways of dealing with infection. Equally important, as I've stressed many times before, is when you get control of this viral population, you have to shut it down. And so now the other thing that happens is, through a whole lot of other feedback mechanisms, the cell detects, okay, threat's over, viruses are gone, we can relax, shut this process down, because if you don't, now you're going to keep on churning out these inflammatory cytokines, and you're going to keep making cells, killer cells, and other sorts of, this is part of the cell's military, and you'll kill off your own guys. So the shutdown phase is terribly important. And if we don't shut this down, now we have the cytokine storm, which we hear so much about. And the cytokine storm is because cytokines and interferons and other antiviral chemical factors will just keep on killing. They're just doing what they were told to do. Now comes in the general and says, right, shut that down. And it does that because now we have a whole series of anti-inflammatory cytokines. We have regulatory T cells that kick in here and say, right, stop all this over here, back over there, shut it down, and life goes on. And then the repair processes, which we saw before, all of those protective mechanisms can now kick in. Now they can detoxify all of the waste material that's there. So it's just quite a remarkable process that we have at our disposal, simply all built in there, quietly working away. And I think it's time each of us really understood that we can have substantial control over how this works in each and every one of us.
Incredible, Christine. It's just wonderful. We spoke about orchestration before, how beautifully it's orchestrated or engineered. It's just, when it's working well, it's so incredibly finely tuned. And look, that wraps it up for today. And I just want to say thank you so very much. It's so wonderful to see these complex mechanisms of cellular biochemistry being translated into such understandable concepts and pictures. So look, thanks very much. And I'm really looking forward to episode 3 in the emerging pieces in the COVID-19 puzzle, when you're going to unwrap some more practical solutions for folk.
Yeah, so we're going to tie it all together in the last episode. There's a lot of science that we've talked about so far, hopefully simplified enough that it makes sense. And then we will get our toolbox out and start looking at how we can influence different parts of these pathways. So thank you again, Robert. It's been a pleasure, and we'll look forward to meeting again soon.
Very good. Bye for now.